Modern cities are remarkable achievements of engineering, but they come at a significant environmental cost. Towering skyscrapers consume enormous amounts of electricity for heating, cooling, and lighting, while their glass facades often trap heat, increasing the need for air conditioning during warmer months. At the same time, dense urban environments produce vast quantities of carbon dioxide through transport, industry, and everyday human activity. For decades, architects have searched for ways to make buildings more energy efficient, yet many structures still function as passive consumers rather than active contributors to environmental sustainability. Now a revolutionary idea is beginning to reshape urban design. Instead of covering buildings with conventional glass, engineers are experimenting with living facades filled with microscopic algae. These photosynthetic systems transform the exterior of buildings into biological machines capable of absorbing carbon dioxide, producing oxygen, and generating renewable energy. The future city may no longer be built entirely from steel and concrete. It may also be alive. The science behind these living buildings begins with one of nature's oldest biological processes: photosynthesis. For billions of years, algae have used sunlight, water, and carbon dioxide to produce oxygen and store energy in the form of biomass. Although invisible to most people, microscopic algae are among the planet's most efficient carbon-capturing organisms. Scientists estimate that marine algae contribute a substantial proportion of the Earth's oxygen production, while removing significant amounts of atmospheric carbon dioxide. Engineers realized that if these organisms could thrive in carefully designed transparent panels attached to buildings, every skyscraper could become an active participant in reducing urban emissions. Instead of reflecting sunlight like ordinary glass, these facades harvest solar energy to sustain living algae that continuously absorb carbon dioxide while growing throughout the day. Unlike decorative green walls covered in climbing plants, algae facades function as sophisticated bioreactors. Transparent panels are filled with water containing carefully selected species of microalgae. Pumps circulate the liquid continuously to ensure that every organism receives adequate sunlight and nutrients while preventing excessive heating. Carbon dioxide collected from building ventilation systems or nearby industrial sources is introduced into the circulating fluid, allowing the algae to consume it during photosynthesis. As the algae multiply, the liquid becomes denser with biomass, which can then be harvested without interrupting the system. Fresh nutrients are added, and the biological cycle begins again. Every part of the process is carefully monitored by sensors measuring temperature, light intensity, nutrient levels, and algae concentration, ensuring optimal performance throughout changing weather conditions. One of the greatest advantages of algae facades lies in their ability to regulate building temperatures naturally. Traditional glass skyscrapers often suffer from excessive solar heat gain, forcing air conditioning systems to work harder during sunny periods. Algae panels behave differently. As sunlight enters the transparent chambers, the algae absorb much of the incoming solar radiation for photosynthesis. This reduces the amount of heat entering the building while simultaneously providing the organisms with the energy they need to grow. During periods of intense sunlight, the algae become denser, automatically increasing the shading effect. When sunlight decreases, algae growth slows, allowing more natural light to enter interior spaces. This biological response creates a dynamic shading system that adapts continuously without mechanical blinds or electrically powered equipment, reducing both cooling costs and overall energy consumption. Perhaps the most fascinating aspect of these living facades is that they produce a valuable asset while cleaning the air. As algae grow, They generate biomass rich in proteins, carbohydrates, and natural oils. This biomass can be processed into several useful products, including biofuels, fertilizers, animal feed, and industrial chemicals. Some researchers are even investigating its use in biodegradable plastics and nutritional supplements. Rather than treating carbon dioxide as unwanted pollution, algae systems convert it into commercially valuable materials through entirely natural biological processes. This creates an economic incentive alongside environmental benefits. Building owners may eventually recover part of their investment through biomass production, while simultaneously lowering energy bills and improving environmental performance. Several pioneering buildings have already demonstrated that algae facades can operate successfully in real urban environments. Experimental projects have shown that living panels can reduce building energy demand while producing measurable quantities of biomass throughout the year. Although these installations remain relatively rare, they have provided valuable engineering data for future developments. Architects are now exploring ways to integrate algae systems into both new construction and existing buildings undergoing renovation. Advances in transparent materials, automated monitoring systems, and water management technologies continue improving efficiency while reducing maintenance requirements. Each new project helps engineers better understand how biological systems interact with architecture under different climates, allowing future designs to become increasingly practical and cost-effective. If algae facades become widely adopted, their impact could extend far beyond individual buildings. Modern cities contain thousands of large commercial structures with enormous exterior surface areas exposed to sunlight every day. Transforming even a small percentage of these surfaces into photosynthetic bioreactors could significantly improve urban air quality while reducing carbon emissions. Dense business districts that currently absorb heat and contribute to urban heat islands could gradually become cooler, healthier environments. Buildings would no longer exist merely as places to work or live. They would actively participate in regulating local climates while supporting cleaner air for surrounding communities. In combination with renewable electricity, electric transport, and improved public infrastructure, photosynthetic architecture could become one of several technologies helping cities achieve ambitious climate goals. The geopolitical implications are equally significant. Nations across the world have committed themselves to reducing greenhouse gas emissions while expanding urban populations continue placing greater demands on energy systems. Traditional solutions often require large areas of land for forests, solar farms, or wind turbines. Living skyscrapers offer an alternative by using surfaces that already exist within cities. Countries with limited available land could integrate biological carbon capture directly into their urban environments without sacrificing valuable agricultural space. This approach could become particularly attractive for densely populated regions where expanding green spaces is difficult. Instead of competing for increasingly scarce land resources, future cities may generate environmental benefits simply by redesigning the buildings they already possess. Despite its promise, photosynthetic architecture faces important technical and economic challenges. Algae require careful management to remain healthy and productive throughout changing seasons. Water quality, nutrient balance, and temperature must all be maintained within specific ranges. Pumps, filtration systems, and monitoring equipment consume electricity and require regular maintenance. Engineers must also prevent contamination by unwanted microorganisms that could reduce algae productivity. Harvesting biomass efficiently while maintaining continuous operation presents another engineering challenge. Initial installation costs remain significantly higher than conventional curtain wall systems, making large-scale commercial adoption financially difficult until manufacturing costs decrease. Furthermore, building regulations, safety standards, and long-term maintenance procedures continue evolving as the technology matures. Researchers are already working to overcome these limitations. Artificial intelligence is being used to optimize algae growth by continuously adjusting nutrient supply, water circulation, and lighting conditions based on real-time sensor data. Advances in materials science are producing stronger, lighter transparent panels with improved durability and insulation properties. Genetic study is identifying algae species capable of faster growth, greater carbon absorption, and increased tolerance to varying environmental conditions. Engineers are also integrating algae systems with heat recovery technologies, allowing waste heat from buildings to maintain optimal biological temperatures during colder months. As these innovations converge, future algae facades are expected to become more efficient, more reliable, and considerably less expensive than today's experimental systems. History demonstrates that revolutionary changes in architecture often begin as ambitious experiments before becoming everyday reality. Steel frames allowed cities to build higher than ever before. Reinforced concrete transformed construction across the world. Double-glazed windows dramatically improved energy efficiency, while smart building technologies introduced automated environmental control. Photosynthetic skyscrapers may represent the next great evolution in urban engineering. Instead of constructing buildings that merely consume resources, humanity is beginning to design structures that actively contribute to environmental restoration. These living facades demonstrate that biology and engineering are no longer separate disciplines, but increasingly interconnected solutions to global challenges. The cities of the future may not simply stand against the skyline. They may breathe with it, quietly absorbing carbon dioxide, producing renewable resources, and helping restore the atmosphere. One microscopic organism at a time. In a world searching for sustainable answers to climate change, the greatest transformation may not come from building more structures, but from teaching the buildings themselves how to live. If you enjoyed this deep dive into the technologies shaping our future, be sure to explore our other documentaries examining the innovations redefining modern civilization. And if you want to keep exploring the biggest questions about science, engineering, geopolitics, and the future of humanity, make sure to subscribe to the channel and join us for the next journey into the unknown.